Okay, so picking up with one more example for intervals of increasing and decreasing, we're going to look at one given a graph. This is important, of f prime. So again, the question here was to determine the monotonic interval. So where's the function increasing and decreasing? This is a very common mistake. Hopefully we do not make it on an assessment. If you are given a graph, pay very close attention to whether the graph is the graph of the function in question, f, or is it the graph of like a derivative of f or a second derivative or something like that, okay? In this case, this is the graph of the derivative of f, and the question is about f. So if you look at this and you answer, well, it's increasing from negative infinity to 1, and then it's decreasing from 1 to 3, and then it's increasing again, that is incorrect, okay? This is the derivative. And remember, our test for finding the monotonic intervals says that if the derivative is positive on an interval, then the function is increasing, and then similarly for negative and decreasing. So when I look at this, I can determine, without knowing the graph of f or values for f, I can determine that f is increasing whenever f prime is positive, and that's happening here and here. So on the interval from 0 to 2 and from 4 to infinity. Once again, these three could be open or closed, but I try to be in the habit of always using open intervals just so I don't accidentally close them for intervals of concavity, which can't be closed. Okay, and then f is decreasing whenever f prime is negative, which is going to be right here, right here and right here. So from negative infinity to 0, and then again from 2 to 4. And one more time, you can use a union symbol in here if you want, which looks like this, which does not look like this. So if you have a tendency to write your union symbols like that, just avoid it and put a comma. All right. So that is intervals of increasing and decreasing, but we can use the same process for determining where a function has local extrema. Okay, and this is called the first derivative test. I know the second derivative test is at the end of these notes, but we are going to skip that until the next section, so you can just cross that off and it'll show up again. All right, so the first derivative test says that here's what the theorem says first. It says if f prime is greater than 0 for every x in the open interval from a to c, and f prime of x is less than 0 for every x in the open interval from c to b, then f of c is a local max. That's a lot of letters and symbols and stuff like that. What do we really mean? We mean if f prime changes from positive to negative, then f of c is a max. Remember, output. Okay. We might be looking for the location, but the value is the output. Okay. And then the other thing is that f of c does have to exist. Okay. I mean, obviously we can't say we can't say f of 2 is a max if f of 2 doesn't exist, but if f prime changes signs, that's what we care about, then we're going to have extrema. So if f prime changes positive to negative, our function changes between increasing and decreasing, so we have a max. If it changes from negative to positive, we change from decreasing to increasing, so we have a min. Notice the way I drew this, f prime of this point does not exist. Doesn't matter. We can have a sharp turn. We just need... And that part doesn't matter. We just need to have a point there and a change in derivative from negative to positive. Okay, so let's do a couple examples here. I am looking at a parabola. So because I know that's quadratic with a leading coefficient that is positive, so I should end up having a min. So let's find this. Okay, so y prime is 2x minus 6. Set this equal to 0. I get x equals 3 as my critical point. Okay, so once again, using a sign chart, not for justification, but for answering the question. All right, so if I plug in a number to the left of 3, I'm going to get something that is negative into my derivative, 2x minus 3, 2x minus 6, or 2 times the quantity x minus 3, and then I have positive here. So if our derivative changes from a negative to a positive, then that means we have a min. Okay, so I have a min at f of 3, which we can go ahead and plug that in, which is 9. Let's see, 9 minus 18 plus 5 is negative 9 plus 5 is negative 4. Okay? And then if it doesn't say to, but if we were justifying, our reason just needs to be because y prime changes from negative to positive. And that is all the explanation we need, okay? All right, on this next one, let's just find the x coordinates for the extrema. We don't need to find the y values. We know how to plug numbers back in. Okay, so once again, start with our critical points. So f prime is equal to 3 times 1/3 is 1. So x squared minus 2x minus 3. Set this equal to 0. Same function as before when we factor it. So 3 and -1 is our critical points. Okay, and again, this is the one we did in the top part of the notes, so we know it's going to be positive, negative, positive. Okay, so that means that because our derivative changes from positive to negative, we have a max at -1, and then derivative changes negative to positive, so f has a min at 3. Okay, so max at x equals -1. Again, my justification, all I need to say is f prime changes positive to negative. Okay, and then min at x equals 3. Okay. So the second derivative test is the last thing on here. We will get to that in the next section, though, because we need to talk about concavity in order to do so.